Hello class. Today we'll talk about the last section of the textbook, which is the mass moment of inertia. The mass moment of inertia appears in dynamics, especially when dealing with rotating bodies. Consider a rigid body with a center of mass at G, and it's free to rotate about a Z axis, which passes through the centroid G. Now if we apply a torque T about the Z axis, the body will start rotating with an angular acceleration alpha. This is angular acceleration. And the relationship between the torque and the angular acceleration is from Newton's second law. It says the summation of all torque applied on the rigid body is equal to moment of or mass moment of inertia multiplied by the angular acceleration. So I is the mass moment of inertia, and abbreviated by MMI. So the moment of inertia, or the mass moment of inertia of a body is the resistance of a body to angular acceleration. So this is similar to the role of the mass in the equation F equal to the ma, where we said in the past that the resistance of the body, translating body, to the acceleration or to the linear acceleration is called the mass. Similarly here, the I, or the mass moment of inertia of a rotating body, is the resistance of the body to the angular acceleration. So the mass moment of inertia is typically used in analyzing rotational motion of bodies, and the Newton's second law for a translating body described by the net force equal to the mass multiplied by the acceleration. So what we know from this, that a rigid body could go either a pure rotation or could go undergo a translation, or combination of both. And that could be in a form of linear or curvilinear or general. So this is called general motion. General motion. This is pure rotation. This is curvilinear. Curvilinear is a kind of translation motion. General motion, curvilinear rotation. And also the special case is, I'm gonna do it here, it's just pure translation. And always we measure them with respect to a point, that point typically the center of the gravity, or CG. Now the mass moment of inertia of a body rotating about the axis is equal to integration r squared dm, or the integration with respect to the mass, and r here is a distance perpendicular to the axis, and or the distance between a mass fragment dm to the axis, and that distance is orthogonal to the axis. The unit of the inertia in SI is kilogram meter square, or in the customary unit is slug feet square. Now, the mass moment of inertia, it's similar to the area moment of inertia, where the parallel axis theorem and radius of gyration has the same definition, except that we replace the area with the mass. In this circumstances, the parallel axis theorem can be defined by IZ, or the moment of inertia about an axis Z, which is parallel to the axis that is passing through the center of gravity of that body, plus the mass distance square, and the radius of gyration, which is k, is going to be equal to square root of the mass moment of inertia divided over the mass. Now, the moment of inertia, or mass moment of inertia, can be obtained by integration or by the method of composite bodies that we learned in the last lecture. So the composite body I can be obtained by using the composite method of bodies that we learned in the area moment of inertia. Okay, the mass moment of inertia is equal to r squared dm if the density is constant across the volume. Because mass equal to density by volume, we can write it by integration of the r square dv over volume. Alright, so how to calculate that? Now let's take some simple problem. Assume we have a cylinder, and that cylinder has a radius r and has a height, say, h. And we have at the center of that cylinder at the bottom is our Cartesian coordinate origin, O. Now, different methods to do that. Now, we need to make sure that we understand what is r squared dv means. Alright, let's take this shell element, which is part of this volume. So I'm just taking it, I'm slicing this cylinder, which is a shell. Now, the shell has a radius, inner radius r, which has a thickness, the wall has a thickness dr. The height is from the bottom to the top, we know as h, and we know that this shell element has very tiny differential thickness dr, so we can assume that the moment of inertia measured from the axis is constant around the z-axis. And the other way is saying that r is r that measures the distance between this shell element to the axis doesn't change. And this is very important. As long as r doesn't change, therefore we can say that the mass moment of inertia of that shell element, which is part of the bigger volume, diz, and this is Iz for this volume, is r squared dm. Okay, where r squared is there, dm is the volume multiplied by the density, and the volume is the circumference 2 pi r multiplied by thickness dr multiplied by the height, right? So that's going to give us 2 pi rho multiplied by the height multiplied by r to the power 3 dr, and this is only for one element, right? Now to do the entire volume, then I have to go from 0 to r. So I z equal from 0 to r, 2 pi rho h r cubed dr. The reason why is to cover this inside area. So this is gonna be 1 over 4 2 pi rho h r to the power 4 from 0 to r, and that is equal to half pi rho h rho square and r square. That over here define the mass of that body, so therefore this is equal to half mass r square. Okay, let's take this example. I want to calculate the mass moment of inertia of this look like a cone, has a height 1 feet, and let's calculate Iz, which is rho r square dV. Now what is r and what's dV? So we're looking at a volume and a distance r. Okay, now assume that this cone is constructed from a series of discs that starts from the bottom all the way goes to the top. So if I imagine there's a desk, definitely this desk has a thickness to, so I'll show it more in detail. This is gonna be my dm, right? Now one thing about this desk, the desk, is that the moment of inertia of this desk, call it moment of inertia, call it the IY because it's a differential of that, is look like the moment of inertia of the desk that we found earlier, where the R in this sense is x, and the mass is not a complete mass, is in fact a partial mass. So it's a dm multiplied by r square from the previous problem, where r square is the radius of that, and that radius is variable, so it's x square, since r square is equal to x square. Now what is dm? Is the mass of that, right? So this has a radius of x, it has a height of dy, and so dm equal to the density by the volume, which is area squared by the height, right? Now not to be confused, we know that x squared, now I haven't really talked about the function here. So say that this function is equal to y squared equal x, so assume that is known. So therefore dy equal, I'm just plugging this over here, dm, so it's rho pi x square dy x squared. Now everything is being integrated with respect to dy, so I need to convert to x squared into sort of y. So since the relation is given to you, but y squared equal to x, then dy equal half rho pi y dy y. I'm sorry, should be we need to square both sides, so this is y to the power 4 and this is y to the power 4, so therefore x squared equal to y to the power 4, right? So I just replaced x squared or x with y squared, and then we have that. So now if I want to calculate the complete mass moment of inertia, I need to integrate both sides. So this is y equal half rho pi, right? The differentiation with respect to y, so it's from 0 to 1, y to the power 8, and that is gonna be equal to I'm just gonna, before I do the calculation or substitution, I'm gonna put this into the perspective of y's. Okay, and over 9, y to the power 9 from 0 to 1, and that is equal to rho pi over 2, 18 over here. Okay, now say rho equal to 5 slug per feet cube. Substitute then IC or IY equal to 5 pi over 18 with the unit of slug feet square. Slug feet square. So the cover page of this textbook has the mass moment of inertia for different shapes: sphere, cylinder, rectangle. This is a common one: cylinder, rod, thin disk, and rings. So let's verify one of these problems, or one of these numbers. Let's say we have a thin plate, and we are interested to calculate the mass moment of inertia of the thin plate about y, which is the resistance of this thin plate to rotate about the y. Now you will notice that sometimes the mass moment of inertia is written by IYY or IZZ or IXX, just to differentiate it from the area moment of inertia, and as long as it's indicated, it doesn't really matter. So let's take this problem and calculate the mass moment of inertia of a thin plate like that one about its y direction. Let's say the y direction is to the right, this is z, and that is x, right? The width is b, the total length is a, and I want to calculate ay or ayy, doesn't matter, ay or ayy same, meaning that how much it is. Now to calculate that, I need to take a strip of element on that. Since the calculation about yy, so it's a density, it's a distance from here to here. Let me clarify this again by taking drawing it only with this is my x, which is r squared, dv, right, dv, and my area, the d volume equal to the area, which is the entire length or width b multiplied by the dx multiplied by its thickness, t. Thickness is from here to here, t. Great. Now r is equal to x, and v, this is b t dx, right? Now the integration is from here to here. The total is a, so this is from negative a over 2 until a over 2. So this is simply rho b t, an integration of x squared is 1 over 3 x to the power 3 negative a over 2 a over 2 rho bt over 3, and that is a over 2 minus a over 2, and this is rho bt over 3. Now this is 8 that becomes a to the power 3 plus a to the power 3 rho bt over 12 a squared. This is mass over 12 a squared, and that's, verify what is in the appendix of the textbook. Alright, so in this problem we'll study the method of composite to solve the mass moment of inertia of a composite structure. So let's say we have a pendulum. This pendulum is made of two parts, typically a cylinder beam and also a plate that has no geometry. Knowing that the centroid of each part of this structure is going to be the middle, assuming this is homogeneous. Now let's say we want to calculate, so the problem is we want to calculate the moment of inertia of this structure about an O, where the axis z is perpendicular to the pitch, simply because this entire structure is swinging. So we want, and this is a swing, as you can see here, on the plane, so it's a swing about the z-axis. So how can we get that? So to get that, we need to find the mass moment of inertia of about O for the plate. So we call this is a plate and we call this is the rod. So this is for the plate plus the mass moment of inertia for the rod about O. So using the parallel axis theorem, the moment of inertia for the plate measured at O is simply its moment of inertia at G plus the mass of it multiplied by the distance, so distance squared, plus the moment of inertia for the rod about an O equal to the moment of inertia of that rod plus the distance mass of it, distance squared. But the problem in the textbook, in fact, it's asks you to calculate the mass moment of inertia about the centroid of this object, right? So I'll make it here simple, and I'm asking it to calculate the mass moment of inertia about an O. So the solution for the one that has that's requesting you to calculate the moment of inertia of this pendulum about the centroid of the structure is given. Here is a little bit different problem. So alright, so now what we need to know is how much is D1, how much is D2, mass 1 and mass 2 are given, and also how to calculate IZ for the plate and IZ for the rod, right? All right. So given, let's say given in the problem that the mass of the rod is just reading from the plate has mass 1 equal to 5 kilogram, and also the rod has a mass equal 3 kilogram. L1 is given by 2. D1. Now D1 is measuring distance from this centroid to here, so this is 2 plus 0.25. So it's a 2 plus 0.25, 2.25 meter, and D2 is simply this distance, so it is 1 meter. The moment of inertia for this cylinder passing through this Z. Now I'm going to use so this is G1 for the rod, right? For the rod. Is should say this is 2. Using the textbook, this is the rod, and since this is swinging and this is the axis perpendicular to the rod, so I'm looking at 1 over 12 ml square. Am I looking at that? Actually, I'm looking at the moment of inertia x bar, right, which is already given to us using the parallel axis theorem, but let's assume that it's given by x 1 over 12 ml square. This is, I know it's the problem already given us or use the parallel axis theorem, so let's assume that we don't have the other value. This is 1 over 12 ml square, right? And this is going to be 2, and IZ G1 for the plate. Now that is because this is swinging. Think of this as swinging about the Z, so therefore we are looking at a combination of in fact it's over here. We're looking at this value, so it's 1 over 12 A square plus B square. Okay, so this, now what we need to do is just substitute values and recalculate. So I'm going to start with the IZOP, right, which is the moment of inertia for the plate about O. I'm just going to plug in numbers from this equation. So for the plate is 1 over 12, the mass 1 is 5, A square, it's 0.5 square plus 1 square, plus, now using the parallel axis theorem to move this from here to there, so that's going to be equal to 5 by distance 1 square, 2.25 square, IZ O for the rod equal, now here's the rod, so it's 1 over 12, mass 2, which is 3, L is 2, right, and this is square, plus using the parallel axis theorem to move this to here, from here to here, that's gonna give us what is the mass multiplied by the distance square. So calculate these, will give us some numbers. Now the total, since both of them were calculated about the same axis, now we can sum that. See, IZ for the entire is just summation of these two. It's gonna be 1 over 2, 12, 5.25 plus 1 plus 5, 2.25 square plus 1 over 12, 3 by 4 plus 3. So that is going to be with the unit of kilogram meter square. Now to calculate the radius of gyration. Radius of gyration is simply defined by K equal square root of IZ about that divided of the total mass plus M2, and this will be whatever this number over the total mass, and the total mass here. So just for completeness, the total mass is 8 and this value is that square rooted, and the unit of that will be in meter. Now in the textbook, the problem is similar, except that it's asking you to calculate the radius of gyration and the mass moment of inertia about the centroid of this structure. So the centroid of this structure is somewhere located between G and O, and the way to calculate that is using the composite structure method for masses, where we first locate the centroid of the plate and multiply it by the mass of that plate, with reference, of course, to let's say Y reference, and also we calculate the centroid of the rod and multiply it by its mass, which is equal to the total mass multiplied by the location of the centroid for all of that. So this goes back to this formula, and I think you guys are all familiar with that method of determining the centroid of areas, volumes, objects, masses. So that's how it should be calculated, and that will be 7.81. Now the problem here is asking you how much is the mass moment of inertia for an axis passing through that point G, not through O. What we solved previously is about O. Now for a problem that involves solving it through its centroid, only change is that you need to calculate or transform or transfer all the mass moment of inertia from the centroid of each single component into the centroid of that structure. So the difference is that you need to make adjustment to the distance over here. So this distance is calculated in reference to the G. So we are moving it there, and then the problem will follow by adding the mass moment of inertia of each component that is already transferred, and then calculate the radius of gyration. So take a look at that. Again, this is going to be the last problem we solve for this textbook, the statics. I hope you all enjoyed the material. I know this chapter 10 requires more time, and that's why we have only the final exam, exam 5, which will be on December 10. Again, this is Thursday from 3 to 5:30. We'll be open only during that time. And the problems are from chapter 10. So study well, and hope to all do well in the exam, and enjoy your holidays and stay safe. Thank you very much.